shouldn't be able to get access to anything else that what I'm already can access legitimately. Um, and the last property that we want to have in such a scheme is that all changes to hierarchy are locally contained in the graph. And what I mean by this is throughout the operation of the system, when after it's deployed, there will be changes to the hierarchy. When we want to add a user class or want to restructure or maybe do something else that we need to do. And if just one portion of the graph changes, you don't want to affect everyone in the system. You don't want to have to go, oh, I'm sorry, we have to change all secret keys right now because we need to introduce some changes. And so it's important that all changes in the graph are locally contained. They don't propagate, they don't affect everyone else. And so the question here is how many keys do we have to have per user class to be able to implement, to be able to do all of these properties. So when we just started working on this problem, we considered different graphs with different structure, different properties. And say, for example, for a tree, it's obvious that a tree can be represented by, it can be totally represented by its pre-order and post-order. All nodes for trees, 2 keys are going to be enough in any case. But later on, if you look at more complicated graphs, it's not really clear how many keys you need to have. But then it occurred to us that if you with just a little bit of public information, you'll be able to do this with just a single key. And it's like, wow, this is just such great result. I mean, it looks like you need only 1 key to be able to do anything for any arbitrary graph. In actually our scheme, it works for any type of graph, even for graphs that have cycles. And it's not that such graphs with cycles are useful in any real life application, but it's not, the scheme is not limited to any particular structure. And here, this is in a nutshell the properties that we have. As already said, we have just 1 key per access class. The public storage space is optimal. And what we mean by this is that you still have to store the access graph, the access hierarchy, but we also store our public information, and it's asymptotically the same as information needed to store the graph. So it's just a small constant that we introduce. All key derivation is based only on hash functions. So this is very fast. There is no expensive cryptography, just hash functions. And all changes are locally contained. And security is, we have provable security against collusions. And we show that any adversary who can corrupt any number of nodes in the graph won't be able to achieve anything else that those corrupted users can already achieve. In previous results had some of this property, but it was the first one to combine all of this together, to have all of them at the same time. So this is a little bit more specific program description, and here you can see that we model this graph. This is a directed access graph, which we call G. And all nodes that correspond to user classes are numbered as V1 through Vn. So there are going to be n classes in the hierarchy. And each node has a set of objects associated with this class, and they're all disjoint sets. And edges are inserted into this data structure according to the relationship between those classes. And we'll just call those edges E1 through EM. And since we need this property so that everyone at a certain class should be able to have access to descendant classes, so if we have an edge from node Vi to Vj, that even if I'm at the parent node, I will be able to derive a key at the child node. So this is just one link. But if there is a longer path in the hierarchy. And if there is a path from node vi to vj, I will be able to have access to that node vj. So you kind of follow this path to get access to the node that I need to access. And so that we say that a key allocation implements a particular access graph J or G if it assigns keys to both users and objects in such a way that a user can access object if and only if that user has a key, decryption key for that object. And so now I would like to talk about the scheme itself. Here it consists of several parts, one of which is key generation. And to generate the key, we need two major pieces. The one piece is private information that is going to be stored on the user side, and another piece is public information that is going to be publicly stored at the server. And private user key, secret key, will be chosen at random for each class. And as you can see here, suppose I belong to a node vi. Then for that particular node, we at random pick a key and call it ki. And it's just a random string of a certain length. In this case, it's going to be raw, which is a security parameter. And so if I'm entitled to access to a certain class, that I'll get a secret key for that particular class. And if I'm entitled to get access to more than one class, separate class, that I'll get a key for each of the classes to which I belong. And this is not, here we're not talking about descendant classes. Here we're talking about completely, different access classes in the hierarchy. For example, I can subscribe to sports, to a sport package, and I can subscribe to movies. And as my sport package will contain basketball and football, and I get access to all of those. And at the same time, I'll get a key to access all movies. And public information associated with this graph consists of public labels for each node. And a label for node vi will be called li. So it's just also a string that uniquely identifies a node, just some label associated with this. And another piece of information publicly stored on the server is one string for each edge. This is kind of hard to visualize this or understand just looking at this expression. But actually, what you need to understand from this is that for each edge, we store some piece of information that depends on both depends on the parent and the child keys for that edge. And so using that information, everyone who belongs to the parent node will be able to derive the key for the child node. And as you can see here, h is a hash function. And this information, the public label stored at the server, is a function of both keys of the parent and child and the child's label. So now we need to see how we derive keys at different levels. So for instance here, suppose that vi is a parent or vj. And so using public information, we can derive the child's key. And this expression is not very difficult. So as you can see, all you need to do, you take your own key, produce a hash, and take your own key and a label of your parent, produce a hash, and use public information to derive the key of the child. And so this is just one link to go from a parent to a child. But if you want to traverse the graph using several hops, you just repeat this procedure with the key that you just derived.